Hello and welcome to my presentation about the numerical case studies about two-dimensional SHS joints with symmetrical and asymmetrical top connection. My name is Patrick Heinemann and I'm a PhD student of the TU Iași. Hollow section profiles are mainly used for industrial purposes or representative structures. These kinds of steel profiles have got many advantages, like their lightweight or high rotational stiffness. By welding two or more members together, a node is created, which is automatically the weakest part of the structure. There are some standards which are defining these nodes, but they have limitations regarding geometry or some other parts, like materials. There's a large difference between uniplanar and multiplanar joints. Today in this presentation I want to show you a numerical analysis of an uniplanar steel joint. It is made out of a vertical pipe, and on the top there are two members connected with a welding line and a different angle. So you can imagine the structure somehow like a column. The steel profiles are squared hollow section profiles, and the load case represents a roof load, so there will be an axial compression load which affects the bottom of the chord, which or the chord is defined as the vertical part of the column. The aim is to figure out the maximum load capacity of the welding line and at the same time an analysis of the maximum deflections. I analyzed 6 different models, and these models can be splitted into 2 groups. The first one is a symmetrical shape, and the second one is defined by an asymmetrical shape. There are different inclination angles. It's 30, 45 and 60 degree. To get comparable results, I homogenized these geometrical parameters, which can be found on the right hand side. On the picture you can see the two braces or branches which are full overlapped. So with other words, the gap which is here defined as G is negative. And connected to these branches is a 5 mm steel plate, and under this steel plate there is a vertical pipe which is called chord. In the literature you can see that the geometrical parameters are most influencing the resistance of these nodes. For my analysis, I picked a cross-section for the chord, which is 120 times 120 times 3 mm thickness, and for the branches there is a 50 times 50 times 2.5 mm cross-section. The material is given with one of the most common steel types in Europe, which is the S235. Now there's the first group, the symmetrical models. On the right hand side, on the top, you can see a figure with an example. In this case, it's a 45-degree model. Besides this, I analyzed a 30 and 60-degree model. The vertical larger member is a chord, and the two connected members are defined as branches or braces. The chord's bottom is affected by an axial compression force, while the braces are set as pinned for the boundary conditions. On the second figure, you can see the welding line. It's a 3 mm fillet weld, which has a three-dimensional shape. So, with other words, the welding line connects the cord to the branches and the branches itself. For the mesh, a 10 mm coarser mesh is chosen with a quadratic tetrahedral element. Around the welding line there's a 1.3 mm refinement, and yeah, you can see it on the right hand side. By looking to the results, you can see that the maximum stresses, von Mises stresses, arises in the welding line, and especially in the corners you can see some stress peaks. You can see it on the first picture. The maximum deflections are in the outer flank of the cord. There's a quotient point, especially for the 30-degree model, in between the two braces, which can be seen in the second picture. It's a blue area. And the maximum stresses are marked as a red area. And depending on the inclination angle, different distribution of deflections arises. The 45-degree model has got, or is the strongest node. With other words, the highest compression force can affect this node. The smallest resistance is there for the 60-degree model, and it's a little bit in contrast to the results of the asymmetrical analysis, which I will present in some minutes. The highest deflection are there for the 45-degree model, but the total range of the results are very close together. Now, the second part is about the asymmetrical models. The inclination angles are set to 30-45 or 30-60 or 45-60. In this case, on the first picture, you can see the example for the 30-60 model. The edge distance is not symmetrical any longer. The load scenario is exact the same like for the symmetrical analysis. So there's an axial compression force for the cord. The boundary conditions, mesh, and analyzation itself is equivalent. The results for the maximum stresses can be seen in the first picture. There's a very similar picture to the symmetrical system. So the maximum stresses are in the welding line and in the edges, especially from the welding line. The highest deflections are at the cord system, and for the braces especially there is the highest deflection for the 30-degree system. The maximum compression force is for the steepest system, and it's a 45-60 system. You can see it here. The graph, or both graphs, for the compression force and deflection have got an increasing trend and have got a similar shape. The delta for the compression force is given with 0.5 kilonewton. And yeah, the system with the highest compression force has at the same time the highest deflections too. Especially for the deflection, the range of the results is very close together. And yeah, the 45-60 model is a little bit in contrast to the 60-degree model. In conclusion, I presented two case studies for symmetrical and asymmetrical SHS joints. There are similar distributions for the stresses and deflections. Nearly the same range of maximum compression forces and deflection can be seen. Partly there are different shape of graphs, especially for the 60-degree symmetrical model, which is a little bit in contrast. There are highest resistance for the steepest joints. And to verify these results, some laboratory tests are needed. Or for the future, I want to analyze more inclination angles, for example, with a step of delta of 5 degree, for example, and I want to analyze different profile types, for example, circular hollow sections or rectangular hollow sections. Thank you very much.